Hello, my name is Siavar Zamani, PhD student from Purdue University, working with my advisor, Professor Aaron Morris. Today, we are going to talk about simulation of drying of droplets and its effect on particles morphology in spray drying. But first, I would like to thank National Science Foundation Graduate Research Fellowship Program for funding this project. A quick overview of spray drying. It is a common manufacturing process for producing particulate materials. Process starts by atomizing a liquid feed through a nozzle on top of the vessel, where small droplets are produced and exposed to hot gas. These small droplets quickly lose moisture and finally turn into dried particles. It is used in a wide range of industries such as pharmaceutical, agriculture, and food. A few example products are baby formula or instant coffee. However, because of the complex nature of spray drying, it is usually run based on a trial and error basis. As you can see by the presented images here, different drying conditions have different effects on the morphology of the dried particle. Our goal is to quantify the effects of environmental condition on morphology of the final product. Before we step into details of our modeling approach, let's go over some important assumptions. First, we will be examining the first phase of drying, when the droplet is still liquid. Second, we consider only insoluble spherical solid particles suspended inside the droplet. Third, we assume the droplet has reached the surrounding gas temperature and the equilibrium evaporation is happening. Our model's main objective is to simulate the onset of cross formation and its rate. To model drying of a droplet, we'll be using a multi-phase flow method known as phase fraction. In this method, wherever a cell is filled with liquid, its value will be 1. And wherever the cell is filled with air, its value is going to be 0. Any cell that has a value between 0 and 1 is going to be our interfacial cell. Our multi-phase flow solver needs to have some required features. Firstly, we will be relying on volume of fluid method because we want to capture the effect of surface tension forces. Secondly, we'll be modeling the insoluble solid particles inside our droplet as Lagrangian particles so we can track their movements. Next, we need to implement evaporation, but we need this evaporation to happen at the interface. That means our model needs to be able to detect this interface and further estimate the area at the interface. And last thing would be a challenge because we'll be using an algebraic advection method. We use the OpenFOAM multi-phase flow solver known as InterFOAM to implement the required features. And once we did that, we modeled the stationary droplet. Now, here the simulation is supposed to be of a droplet with no gravity, flow, or evaporation. What we need to see is a droplet with no movement whatsoever, whether inside of it or outside. What happens instead is that we observe these internal parasitic velocities, also known as spurious currents. These flows are solely due to numerical errors creating unphysical velocities inside and outside of the droplet. The reason this happens is that we are performing in a very low capillary regime. What I mean by low capillary is that we are using water as our liquid. That means it has a very low viscosity and a high surface tension. And for our case, the velocity is almost nearly 0. In these conditions, what becomes important is the surface tension force. Now, any small error in surface tension forces will lead to the unphysical velocities that we saw. And in this case, the curvature estimation that InterFOAM uses is not accurate enough. So for the past couple of months, our main efforts have been spent on improving curvature estimation in OpenFOAM. A better way for estimating the surface curvature is using height function method. Height function adds the amount of liquid surrounding the target cell to reconstruct the surface locally. In 2 dimensions, the resulting surface will be a line. Then we can use calculus to accurately measure this radius of curvature locally. Presented here are 2 droplets that are being simulated by using 2 different methods. On left, we are using the OpenFOAM native solver InterFOAM, and on the right is our modified 3-point height function method. And as you can see, the error is present in the left droplet, while we have no unwanted or unphysical velocities in the right droplet. That means our method is successfully working. Next, we tried extending the height function method to 3D. However, in 3D, instead of reconstructing a line, we'll be reconstructing a surface. On this surface, each point is representing the addition of the height of the liquid in the respective column. Once we implemented the 3D height function method in OpenFOAM, we realized that due to the poor accuracy of the advection method, the surface is going to be extremely noisy, and a 3-point interpolation scheme is no longer sufficient to capture the true curvature of the interface. Let's look at the x-axis here only. Here you can see that at cell 2 we are getting a positive radius of curvature, while at the next cell we are getting a negative one. This will lead to the unphysical velocities that we have been trying to avoid. Let's use the line used in the previous slide as an example. We know that for this specific line, the true radius of curvature is negative 46.875, and we will be using this point as our target point. Next, we'll be creating a 3-point, 5-point, and 9-point interpolation schemes to see how accurate we can get. However, as you can see, by increasing the number of points, we are not getting any better results. So in order to capture the true radius of curvature, we use a least square method. You can see that using a least square method, we drop the error from 300 to around 5%, and we also get the correct sign for the radius of the curvature, which is necessary. Our modified height function method for 3D is a combination of polynomial and least square method. As you can see here, for the center lines we are using least square, while for the corner points we are using polynomial fit. Just to give you an idea, a 5 by 5 fourth degree polynomial uses 225 points, while our method, giving far better quality, uses only 189 points. One point is that in order to be able to use this method, you need to have access to a larger memory to be able to parallelize the simulation. On the left, you're seeing a droplet in 3D containing solid particles. On the right, you're seeing a slab of the said particle cut in half. On the next few slides, I show you the results of 3D simulations, but that is going to be of the XY plane of the shown slab here on the right. On the left is the droplet in 3D modeled using the OpenFOAM native solver, and on the right is our modified height function method in 3D. And as you can see, again, on the left, we are having the unphysical velocities, and on the right, we have totally eliminated the unphysical velocities. That means our method is working successfully in 3D. Once we eliminated the unphysical velocities from our simulations, we implemented the evaporation model, and as you can see here for a 3D case, we have uniform evaporation where solid particles accumulate on the surface of the droplet. In order to verify the accuracy of our simulations, we developed an analytical model to estimate the accumulation rate of solid particles on the surface of the 3D droplet. The model is based on the evaporation rate, particle number density, size of one particle, and the packing limit in the wall effective volume. Using the data presented in the table on the left, we compare the results of the analytical solution with that of our computational model. A few points to highlight. First, using the data, the estimated actual number of particles in the droplet is about 9.4 trillion. And in our simulation, we have used 1 million representative particles. Second point is that the cross thickness represents the accumulation of particles on the surface, and here it has been non-dimensionalized by the diameter of one solid particle, which is about 100 nanometer. As you can see from the graph, analytical and simulation results agree together, verifying that our model works correctly. So far, we have only focused on uniform evaporation imposed on a droplet without any airstream. However, we know that for a droplet in an airflow, evaporation, being a function of vapor and static pressure among many other factors, will not be uniform. Therefore, we will now examine an extreme case of non-uniform evaporation to to test if our method is capable of handling it. Before I start the simulation on this slide, let me explain what's happening. We'll have the simulation starts here and nothing happens for a while. Then evaporation is activated on the left side of the droplet as shown by the green line here. Note that on the right side of the droplet nothing happens, and then evaporation stops. This way we can see how the solid particles inside the droplet will move. We can see that the droplet is shrinking from the left side, and now the evaporation stops. And the solid particles inside the droplet along with the droplet will move to the left. To visualize this better, let us isolate only solid particles before and after evaporation. In this slide, we have removed the fluid from the background and have kept only solid particles. On the left side, we see the uniform placement of solid particles inside the droplet before the evaporation, and on the right side, we see the particles position after the non-uniform evaporation. What is interesting is the accumulation of particles on the surface where we had active evaporation. To quantify the effect of non-uniform evaporation on particles' movement inside our droplet, we use particle non-uniformity. This is the ratio of number of particles on the left half of the droplet to the total number of particles, and we are varying evaporation rate to see how this number changes. Here, the x-axis is time and the y-axis is particles non-uniformity. Note that at time equals 0, it's 0.5, meaning we have equal number of particles on the left and right halves. And you can see by increasing evaporation rate, more and more particles are drawn into the left half of the droplet where we have active evaporation. And once the evaporation stops, particles stop moving as well. To understand the effect of droplet viscosity on particles' movement, we repeated the same simulation but kept the evaporation rate constant and used different liquid viscosities instead. Here, we can see that for values less than 0.001, viscosity has little to no effect on particles' movement. We can conclude at this length scale, surface tension force is the dominant factor. For values above 0.01, however, viscosity prevents particle movement. In summary, we have created a solver that incorporates Lagrangian particles, interfacial mass transfer, and most importantly, we have eliminated a spurious current and created a model that functions accurately for cases with low capillary numbers. For future work, we would like to include a species equation and implement a vapor gradient-based evaporation method. Thank you for listening to my presentation, and please reach out to me if you have any questions.